Hello everyone. Welcome to the HSC Physics April 8 Notes lecture presented to you by, of course, 8 Notes. Welcome to the lecture. I hope you guys had a very enjoyable long Easter holiday, weekend. And obviously you guys are on school holidays right now, so as year 12, so I hope you guys are making the most out of it as you enter into term 3 or your third term of year 12. So yeah, this lecture is brought to you by 8 Notes, and before we get into the actual lecture, I'd just like to start off by introducing a little bit about myself. So, hello everyone, my name is Thamika. I graduated from North Sydney Boys in 2022 with an ATAR of 99.30. Currently, I'm studying medicine all the way in Queensland, and in terms of the subjects that I'm doing chemistry. I did chemistry, physics, 3 maths, so maths advanced and maths extension 1, English advanced and English extension 1 as well. So 10 units overall. In terms of my hobbies, or you can see a bit about my hobbies over here, Bed Wars, Valorant, and also playing piano a little bit. So now I'll give you a little bit of info about 8 Notes for those of you who are just discovering about these free lectures that we offer. So since 2007, we've been offering heaps of free resources to make sure students just like you can thrive in their studies. So we've offered free lectures just like these ones since 2015, and these free lectures are in line with 8 Notes' mission to help students as much as possible. And we have tons of free resources for you, as you can see on this slide. So this slide shows some of the things that we offer, and you can find pretty much everything at 8notes.com. And if you want more info or tips on how to use these resources, check out the info doc under the resources section of this lecture page. And well, in terms of the free resources that we have free notes, free videos, free guides from past students. And if you have any questions after the lecture as well, you can go to the online Q&A over here where either past or current students just like me can answer your questions. And if you're looking for even more support, we've got you covered. So here are some of the more resources that we offer. So we offer low-cost group and private tutoring via TuteSmart, printed study guides, and also online access to study resources through Ed Unlimited. And finally, I would like to thank all of our partners, as you can see on this slide, for helping us make these lectures happen. Now, with that said, we can get into the actual lecture overview. So we're going to be going through Module 7 in this lecture. It's a pretty chunky module, fair warning, and it's not exactly in syllabus order, but everything that you will need, or like all the general info that we cover, all the main topics that you will cover in Module 7 are all listed over here. So in our first hour, or maybe less than an hour, we'll aim to cover through the electromagnetic spectrum, the wave model of light, and the quantum model of light. So within this block 1, we'll be going through the development of the models of light, the wave behaviors, and blackbody radiation. And learning about blackbody radiation will then, segue us nicely into the second block, which will be looking at the quantum model of light and special relativity, which will then, I'll be flexing Einstein's gigabrain. In terms of what we're learning in the second block, we're going to be looking at the photoelectric effect, spectral analysis, Einstein's postulates, and the energy mass equivalence. And also, now before we get into the actual lecture, quick disclaimer is, with this lecture, it's only 2 hours long, right? Don't feel too bad if you don't understand every single minute detail about Module 7. Obviously, the purpose of this lecture is to get you guys to understand the general concept so that when you do actually end up learning it in school, it'll make a lot more sense to you. And that's especially the case in terms of special relativity. So I'll try with this lecture to get you guys to wrap your minds around special relativity, because the thing is, thinking about special relativity, it kind of breaks your mind. So it's very trippy. So I hope my hope is that with this lecture you'll be able to understand a little bit about special relativity and the logic behind special relativity that Einstein thought of as well. So yeah, don't feel too down if you don't get every single question or something. Obviously, you do have the chance to go through the lecture slides or rewatch these videos. The main important thing is to make sure that you understand all the concepts. So also don't make you have the lecture slides down below. So don't waste time taking down notes and everything. The main important thing is to make sure that you guys understand these concepts. So with that said, let's go into a little bit more about how you'll be analyzing what we have in the lecture, right? So the words in red, they are keywords. So you should be able to define these, because these keywords can be tested on in your exams. And the words in red are also general concepts that if you know how to define them, then it shows that you have a good understanding of those concepts, which is what we're looking for. So the other important thing is this is a whole module in 2 hours. So as I mentioned before, it's okay to not understand everything, and we're just giving you a foundation so that learning later will be easier. So with that said, let's get into electromagnetic radiation and electromagnetic waves. So most of you will know that light, we consider it an electromagnetic wave. And if you see over here, it's in red. So we need to ask ourselves, what exactly is an electromagnetic wave? Can I define what an electromagnetic wave is? So if you look over to the bottom of our slide, well, we've defined an electromagnetic wave as a wave consisting of electric and magnetic fields oscillating at right angles to each other, which can self-propagate through empty space. So empty space indicates that it doesn't need a medium to travel through. And we know that electromagnetic waves, as per the name, has an electric and magnetic field within it. So this is what it would look like. And if we see over here, if we look at the axes now, the electric field is, if we're trying to think about it in axes, right? The propagation direction, we'll consider this the Z axis, so into the page. The magnetic field is the X axis, so it's perpendicular. So the X axis is perpendicular to the Z axis. So the magnetic field is oscillating perpendicular to the direction of propagation. And the electric field is in the y-axis, which is perpendicular to both the x and z axis. So everything is oscillating, or the electric field, magnetic field, and direction of propagation are all perpendicular to one another. This is also a good definition for electromagnetic waves. And the important things to consider about this definition is you need to make sure that you state that it consists of both an electric and magnetic field. You need to ensure that you say that they oscillate perpendicular to each other or at right angles to each other. And you have to make sure that you mention that electromagnetic waves can self-propagate. So we'll look at this process of self-propagating in a bit. So now let's go through what it means, to what we mean by self-propagation. So we have some dude called Maxwell, which we'll go through in a bit, but basically he created four laws. So here's the thing. So these 4 laws allow us to understand why an electromagnetic wave self-propagates. And by self-propagates, we basically mean that it makes itself move. So it creates itself basically. So it propagates itself basically. It keeps itself moving. That's what we mean by that. So let's look at how this works. So a point charge produces an electric field. So that you guys should understand that if I have a proton, the proton will create an electric field. And an accelerating point charge now, it produces a changing electric field. That's following Gauss's law, which is one of the laws that we will talk about or unpack in a bit. But for now, you guys should just follow through what this means. So an accelerating point charge produces a changing electric field. A changing electric field will produce a changing magnetic field following Ampere's law, and now following Faraday's law, a changing magnetic field produces a changing electric field. So if a changing magnetic field produces a changing electric field and a changing electric field produces a changing magnetic field, then these last 2 steps will just occur in a cycle, right? It's just a repeating loop, an ongoing loop. And as these last 2 steps repeat, that is how the process of EM wave self-propagating occurs. So this is how the process of self-propagation occurs. So with this, as long as you guys understand this logically, then it should make sense. The most important part is the first 2 steps in terms of memorization. You need to be able to link the fact that an accelerating point charge produces a changing electric field. So this is how electromagnetic waves self-propagate. Now, a little bit of a summary about the electromagnetic spectrum. So obviously we have radio waves, microwaves, infrared visible light, ultraviolet, X-rays, and gamma rays. And the energy increases as we go from radio waves to gamma rays, and in terms of how much they can, like the wavelength. So, approximately scale of wavelength is buildings, humans, honeybees, needlepoints. So obviously the wavelength keeps on decreasing as we go from radio waves to gamma rays. So that's a little bit of a summary about the electromagnetic spectrum, which you would have gone through in year 11. So now let's talk about this guy, Maxwell, which I mentioned earlier. So these electromagnetic waves were first predicted by James Clerk Maxwell. And if you look over here, his name is in red. Well, what does that mean? It means that James Clerk Maxwell can be tested upon in your HSC questions. So how much detail can they test you on? Well, these 3 points that we have down here, that's about as much detail as they can test you on. We don't do case studies and depth studies on what Maxwell did in his life, but there is one important thing that has significantly contributed to our understanding of HSC physics particularly, and so that is what they're going to test us on. So what he did was he put together 4 equations to unify electricity and magnetism for the first time. And we came across some of these 4 equations over here. So Gauss's law, Ampere's law, this was some of his 4 equations. So what he did was he put together the 4 equations to unify electricity and magnetism for the first time. Now, you don't need to know these 4 equations. You don't need to be able to, know the equations for these. Like, you don't need to be able to write down these 4 equations. You just need to know that he put together 4 equations to unify electricity and magnetism. What else did he do? Well, he described these electromagnetic waves as self-propagating waves with electric and magnetic fields oscillating at right angles to one another. So our definition for electromagnetic waves comes from his description of it. And he also rearranged the equations to predict that electromagnetic waves should travel at a speed given by 1 over these two constants, so epsilon and mu naught, which is approximately equal to 3 times 10 to the power of 8 meters per second. So he gave light to travel at a speed given by this, which is always a constant if you see it, because this and this are both constants. So if you look over here, the speed of electromagnetic waves is always a constant, and this will come back to haunt us basically when we learn about special relativity. But for now, we don't need to worry about it too much. All we need to know is that he predicted that EM waves should travel at a speed of 3 times 10 to the power of 8 meters per second. Now, what else did he do? Well, he did also influence our understanding of light. He also predicted that light was probably an electromagnetic wave, and he predicted thus the speed of light as well. He never validated that the speed of light was as such. All he did was he predicted that light was an electromagnetic wave that traveled at 3 times 10 to the power of 8 meters per second. He mathematically predicted that, but he never validated this to be true. So that's a little bit about Maxwell. As long as you remember this stuff and what I just mentioned about light, you should be okay to answer most James Clerk Maxwell questions. And so with that, we segue very nicely into our first question, which is a Nessel sample question. So James Clerk Maxwell made significant contributions to physics. Which of the following did Maxwell not contribute to our understanding of physics? So let's go through all these options. So option number A, predicting the velocity of electromagnetic waves, predicting the existence of electromagnetic waves, validating the existence of electromagnetic waves, and unifying electricity and magnetism through equations. So let's go through this. So let's go through we'll go from A, B, C, D. So let's go through option A. Did he predict the velocity of electromagnetic waves? Well, he did, right? He rearranged the equations to predict that electromagnetic waves should travel at a speed given by 3 times 10 to the power of 8 meters per second. Now let's go through option B. He predicted the existence of electromagnetic waves. Well, did he do that? Yes, he did. So what he did was he described electromagnetic waves, and he also predicted the existence of electromagnetic waves. That's also another thing that he did. Did he validate the existence of electromagnetic waves? Well, no, the answer is no. So the answer for this question is C, but let's go through option D as well. Did he unify electricity and magnetism through equations? Well, if we read our first dot point on the previous slide, he put together the 4 equations to unify electricity and magnetism to obtain what we now know as the laws of electromagnetism. So did he do that? Well, he did. So he did option D, he did option B, he did option A, he didn't do option C. So what he didn't contribute to our understanding of physics was validating the existence of electromagnetic waves. All he did was he predicted the existence of them. So our answer for this is option C. Now let's go through measuring the speed of light. So the speed of light has been measured many, many times by various physicists over the years. So although Maxwell predicted that EM waves should travel at a speed of 3 times 10 to the power of 8, and he predicted that light was an electromagnetic wave, a lot of people, even before Maxwell, tried very hard to determine the speed of light using many different apparatuses, and they had varying degrees of accuracy on them. So the first one that we'll learn about is, so these are all historical methods of measuring the speed of light. In terms of the questions that you'll get regarding how people measure the speed of light, you'll get 2 different types of questions, right? So you'll get, and these will all be like, there's no calculation question. Okay, never mind. There are some calculation questions on this, but most of the time, the questions that you'll get for questions regarding measuring the speed of light, this is an entire dot point on itself, by the way. So most of the questions that you'll get for measuring the speed of light will be asking you guys to compare or describe one of these measurings of the speed of light, or maybe compare one historical and one contemporary method of finding the speed of light. Contemporary methods are, lasers and using lasers and stuff, and other machinery. They could also ask you to because the apparatuses were relatively simple and not as complicated as machinery nowadays. They'll also ask us to, use their equations. So they'll give us an apparatus, and they say use Fizeau's or Foucault's apparatus to calculate the speed of light. So, or how fast would they have to operate their mechanism or the contraption to calculate the speed of light. So those are some calculation questions that might come, but they won't be too bad, because as long as you know how their setup worked, you should be okay with calculating the speed of light based on the apparatus. So the important thing is to know their concepts, because they can ask you to explain Galileo's method of calculating the speed of light. So now we can segue onto the different methods of calculating the speed of light. So the first one that we'll learn about for the historical methods is Galileo. So he was kind of crude in his way of measuring the speed of light. So what he did was he got his him and his buddy. So I'll say Galileo's G. His buddy is is B. So there's G and there's B, right? So Galileo went up to one mountain, and then B, his buddy, went up to another mountain that was approximately the same altitude, and they're around 1 to 10 kilometers away. Obviously, they can't be too far away, otherwise Galileo can't see his buddy B. Basically, I think they were like around 1 kilometer away. That would make more sense. But yeah, Galileo was 1 kilometer away from B, and what he did was he had a lamp, and he had a timer, right? So what he did was and the lamp was covered with a cloth or like something that was obscuring the light. So what he did was Galileo was the only one that had the timer, right? So what he did was he gave B a lamp as well. So now there were two lamps and one clock. And what Galileo did was he uncovered his lamp, and he waited until B could see the light from his lamp, right? And when B saw the light from Galileo's lamp, B would uncover his lamp as well. And Galileo would calculate the time taken for the light from B's lamp to enter his eye. So basically, Galileo would start the timer as he uncovered his lamp, wait for the light to reach B, then B would uncover his lamp, and then Galileo would wait for the light from B's lamp to enter his eyes, and then he would turn off the timer. Now, fun fact, light can travel around the Earth 7 times in 1 second. So yeah, and the circumference of the Earth is a lot more than 1 kilometer. So obviously the time taken for light to travel the 2 kilometers, so two ways, so one kilometer to B and then 1 kilometer from B to G. So the time taken for light to travel 2 kilometers is going to be very, very tiny. So this, like, the validity of his experiment was very, very bad, because one major error that gives it one major error is human time, or like the human reaction time, right? And human reaction time itself is going to be like 100 or maybe even 1,000 times more than the time it takes for light to travel that 2 kilometer distance, right? So the answer that he got, or like the value that he got, was like approximately 100 times or maybe 10 times faster than the speed of sound. So it was very, very inaccurate. And it was also a really bad historical method, but because it's so goofy, it's also the easiest to remember. But I would recommend not talking about this if they ask you a 5-marker to explain like the things, like one historical method of measuring the speed of light. I'd probably ask you to talk about Fizeau or Foucault, which we'll go through. But yeah, Galileo is like the easiest one to remember. And in terms of its limitations, as I mentioned before, the main limitations was like human reaction error, or human speed, or human reaction speed, and also if it's like cloudy or something, or if he stands too far away, then the bending of the Earth will cause the light to like not reach him and stuff. So yeah, there's a lot of errors with his like method. The next one is Romer. So Romer, what he did was he used the orbit of one of Jupiter's moons, which to calculate, and the difference in time. So how the Earth orbits around the sun. So as the Earth is further away from Jupiter, the time taken for the eclipse to occur is greater than the time taken for the eclipse to occur if Earth was closer to Jupiter's moons. So he used that difference because he knew the circumference of the Earth and the circumference. So he knew the diameter of the Earth, a crude estimate for the diameter of the Earth. So he used that value to calculate the speed of light, that difference in time, which is about 11 minutes. He used that to calculate the speed of light. He got a pretty decent value, and the limitations for this was he was held back by the current understanding of the accurate dimensions of the speed of the circumference of Earth and stuff. So the measurements conducted at that time weren't accurate enough for him to use his calculations properly. So that was kind of the main limitations about Romer. And then we also have Fizeau. So Fizeau and Foucault, who was an improvement of Fizeau, were quite accurate in their calculations for the speed of light. So what Fizeau did was he had a very clever setup involving a rotating cogwheel. So a rotating cogwheel has teeth and gaps between the teeth, right? So that's what a cog looks like, a cogwheel. So it has teeth and gaps between the teeth. So what he did was he set up the apparatus such that a light source would shine light through the gaps between the cogs within the cogwheel. So I'll call the cogs teeth, right? So there's teeth and then there's gaps between the teeth, right? So what he did was he set up a cogwheel so that the light source would shine a ray of light through the gaps between the teeth, and it would hit a mirror like 10 kilometers away, right? And then it would hit a mirror 10 kilometers away and then come back. And as it was coming back, what he would turn the cogwheel slightly so that as that light ray was coming back now, instead of it going through the gap again between the teeth, it would now hit the adjacent tooth to the gap that it passed through. So it would pass through a gap, then he would turn the cogwheel slightly, and as the light ray was coming back, it would hit the tooth, and then we would see no light because we're standing behind the light source, right? So he did this. So basically, you'd have to turn the cogwheel. You'd have to turn the cogwheel faster and faster and faster until he reached a speed, a rotational velocity that would completely block out all of the light rays that light source would send. And what he did was he now knew, he knew the rotational velocity, and he knew the distance taken for the distance that light would travel. So he could calculate the time taken for light to travel the distance. Then he would do distance over time, and using that, he would calculate the velocity of the speed of light. So he had a pretty accurate setup. The main limitation with Fitzgerald's method was that, at his time, the technology available to him was limited as opposed to what we have right now. So that was probably the main limitation, because his method was quite a clever and quite a good setup in terms of using it to measure the speed of light. And then we also have Foucault, which was an improvement on Fitzgerald. So Foucault was an improvement on Fitzgerald. He, instead of using a cogwheel, he used a rotating mirror. So he had basically, as light would hit a rotating mirror, get reflected upwards, come back down, and then he would rotate the mirror slightly so that when the light came back down to hit the rotating mirror, it would get reflected at an angle, and he would calculate that angle, and he would know all the values, and using that, he'd be able to calculate how fast light would travel. And that's what he did to calculate the speed of light as well. And other people since then have also had experiments to measure the speed of light, but the four that I just mentioned are the major ones that you'll be covering in the module 7 physics module. Right now, for contemporary methods, we use lasers and superposition to calculate the speed of light. So now we use machinery like oscilloscopes and stuff to calculate the speed of light. So that is the topic on measuring the speed of light. Now we can move on to the development of the light model. So I like to think of this as a story. So, the difference, how we came to treat light the way it is. So, originally, right now we think light is a wave particle duality. So it's, exists as both, so it exhibits both wave and particle properties to a degree. But before, we considered light to be a particle, we considered light to be a wave. So it was an entire journey for us to get to where we are. So that's kind of what I like to think of it as. And me visualizing it like that allows me to now, remember everything that happened. Because initially everything was all a mess. So we have to think of the particle model, the corpuscle model, the wave model, the quantum model, so much things, right? But now it makes a lot more sense because I like to think of it as a story. So let's look at the development of the light model initially. So initially there was a lot of doubt as to whether light was a wave or whether it was a particle. And the two people that was leading this debate as to whether light was a particle or a wave was Newton and Huygens. So Newton, Sir Isaac Newton, believed that light was made up of particles, and these particles were called corpuscles. That's what he believed. And he believed that these corpuscles were attracted to mass. So as they would enter a more dense medium, they would, speed up, basically. That's kind of what he thought. He thought that these particles called corpuscles were attracted to mass. And Huygens believed that light was a wave. So, two different opposing views, and a lot of debate went on, and a lot of things happened that ultimately led to, as you would know, which you've learned in junior high school and even year 11, you learned that light is a wave. So obviously at some point in time, this corpuscular model of light was discarded, and that was due to some experiments that happened. So this was that initial debate as to whether light was a particle or a wave, and Newton or Huygens were the people who are leading this debate, basically. So so standard wave behaviors like reflection, refraction, and diffraction, they could all be explained by both models. But less standard behaviors like polarization and interference could only be explained by the wave model. So this thing was an aspect of the wave model that gave it a edge over the corpuscular model, because the corpuscular model, it struggled with or could not explain polarization or interference. And you can see that these are all in red, right? So corpuscular model, you should be able to explain that, the corpuscular model indicated that was a model of light that indicated that light was made up of particles or mass attracting particles called corpuscles. That's kind of what the corpuscular module of light is. Reflection, refraction, diffraction, these are wave properties that were done in module 2 of physics. So these you guys should be able to define as well. So the thing is, standard wave behaviors like these could be explained by both models, but other like less standard or more complicated behaviors like polarization and interference, which we will go through. So polarization you guys might not have gone through yet. Same with interference. We'll go through that in a bit. They could only be explained by the wave model. So let's look at polarization now. So what is polarization? Well, polarization, it refers to the direction, like the polarization of light refers to the direction of oscillation of its electric field. So what does that mean? Well, normally light, like light from the sun, for example, it's unpolarized. What does that mean? That means that light from the sun, for example, unpolarized light will oscillate in infinite like planes. So in infinite directions, basically. So if you see over here where my cursor is, that is unpolarized light. So light can oscillate vertically, horizontally, and any amount of degree within that horizontal and vertical axis as well. So you can oscillate diagonally in any magnitude, for example. So yeah, unpolarized light is very messy, so it can oscillate in any possible direction as that they want to. What we do using a polarizing filter is we polarize the light by now setting a polarizing direction, so that light will now only oscillate in one direction. So as unpolarized light passes through a polarizing filter, we restrict the axis of polarization so that it will only polarize, or it will only oscillate, in one direction. So you can see over here, unpolarized light enters a polarizing filter with a vertical axis. So it's got a vertical polarizing axis. And so now as it passes the polarizing filter, only the light that oscillates in the vertical axis will be able to pass through. So only the light that oscillates in the vertical axis within unpolarized light passes through. And so now we only have plane polarized vertically oscillating light. So we call these waves that have passed through the polarizing filter plane polarized. And so now it can only oscillate in one direction, which is the direction of the axis within the polarizing filter, which happens to be vertical in this case. So that's how polarization of unpolarized light occurs. Now let's go to polarization of unpolarized light. Now let's go to polarization of polarized light, which we'll go through in a bit. Let's go through the equations to calculate the polarization of unpolarized light. So obviously now there are questions that they can ask, or they'll give you an intensity of unpolarized light, and they'll ask us to calculate the intensity of the polarized light after it passes through a filter. So how do we do that? Well, it's in the next slide. So we have I is equal to 0.5 I naught. So let's unpack this. What is I naught? I naught is the initial intensity of light. So it's the initial intensity of light, or in other terms, the intensity of the unpolarized light wave. So this I naught is the intensity of this light wave over here. And what is I? Well, I is the intensity of the light leaving the polarizer. So it's the intensity of the now polarized light. So I refers to the intensity of this light wave. And if you now look at this equation, it's basically saying that the intensity of the light leaving the polarizer, so the intensity of this light wave, is half the intensity of the light hitting the polarizer. So this light wave will have half the intensity of this light wave. So the polarized light will have half the intensity of its unpolarized counterpart. That's what it's kind of saying. And now let's go through the polarization of unpolarized light. Now let's go through the polarization of polarized light. So say now, let's go through this picture. Say now this vertically polarized, this plane polarized light over here. So it's the same light wave. So this vertically polarized, plane polarized light, say it now hits like an analyzer or a polarizing filter at an angle of 45 degrees. Then the light will get polarized again, and it will now only a certain amount of intensity of light will pass through this 45 degree oscillated light. So how do we calculate what the intensity of the light leaving a polarizing filter is when plane polarized light enters the filter? We follow Malice's law. What is Malice's law? It's I is equal to I naught cos squared theta, and I naught and I are the same as before. So I naught is the initial intensity of the light. So this time it's going to be the polarized light before it hits the filter, and I is going to be the intensity of the light leaving the filter. So it's the light polarized by so the light leaving the polarized filter. I naught is the already polarized light entering the filter. So I naught is before the filter, I is after the filter. And we add cos squared theta now because I is going to be smaller than I naught, right? So the intensity of the light leaving the polarizing filter is going to be less than the intensity of the light that's coming in before the filter. So we follow Malice's law, and this theta is given by the degree that I naught, or the degree that the polarizing filter is at. So if the analyzer is set to 45 degrees, then to calculate it, we do I is equal to I naught cos squared 45. So that's how we would calculate that. And if we're going to calculate it now, say we're set to 45 degrees, the intensity of the light leaving this, so the intensity of this light wave over here is going to be half the intensity of this light wave over here, because cos 45 squared is equal to a half. So now let's move on to a little bit more about polarization. So now the first question. So unpolarized light is passed through a polarizer so that it is now plane polarized in the vertical direction. As it leaves, it passes through a second polarizing filter. At what angle should the direction of polarization in the second filter be so that no light passes through? So if no light passes through, what does that tell us about the intensity? It tells us that the intensity is going to be 0. So we want I now, we want this light leaving, the intensity of this light leaving, we want I to be 0. And it doesn't give us I naught, so we don't care about I naught, but we know that it's going to be polarization of already polarized light because we have plane polarized light and we let this plane polarized light pass through a second polarizing filter. So now plane polarized light is being polarized again, and we want the second polarized light to be 0. So we let I is equal to 0, and then we solve this equation to find the theta, to find the angle at which I is equal to 0. So let's do that now. So we write down our equation, I is equal to I naught cos squared theta. Then we let I is equal to 0, so I naught cos squared theta is then equal to 0. So then we let cos squared theta is equal to 0 because I naught won't affect our answer. And so we let theta is equal to 90 degrees. So we get our answer of theta is equal to 90 degrees because if we do cos 90, we get 0. So cos squared 90 is also going to be 0. And what does that tell us? Well, that tells us now some general information, right? So if the polarizing filter is perpendicular to the direction, if the slit in the polarizing filter is perpendicular to the direction of our plane polarized light, then no light will pass through. That's what it tells us, right? If it runs perpendicular or at a 90-degree value to the direction of polarization of our plane polarized light, then the intensity of light leaving our polarizing filter, so the intensity of our second polarized light wave, is going to be 0. That's what that tells us. In terms of what you should be looking out for in polarization type questions, the most important thing and the most important place where I've seen many students make mistakes is they fail to identify whether we used this equation or this equation. So a lot of students, they hammer in Malice's law into their minds, and so when they read a question, they instantly look at Malice's law, and some questions they'll trick you by making you think that it's passing through a second polarizing filter when in reality it's the polarization of unpolarized light. So make sure that you check whether you're looking at the polarization of unpolarized light or the polarization of already polarized light, because there's two different equations that go for each of them. All right, so that's polarization in a nutshell. Now let's look at wave behavior. So diffraction and interference. Well, what is diffraction? Think back to year 11, module 2. Diffraction is when waves bend around obstacles. So this is diffraction over here. So as it enters the slit, it becomes a point source wave, and it starts now basically spreading out from this one point source. Same with over here where it bends around this obstacle over here. This is an example of diffraction. So you should be able to define diffraction because it is in red. Now let's move on to wave interference. So let's look at wave interference. Now, what is wave interference? Well, wave interference is when waves meet together and they collapse into a single wave. That's what wave interference looks like. So let's look at wave 1 and wave 2. What happens when these two waves interfere with one another? Well, if you can look over here, their crests align, their troughs align as well. So, and they have the same wavelength and same amplitude. So what happens is we add these two waves together to form constructive interference because the waves are in phase, because their troughs and crests align. So these waves are considered to be in phase. So when we add it together, the amplitude gets doubled. The wavelength stays the same, but the amplitude gets doubled. So now it becomes a bigger wave basically. So we undergo constructive interference to form a bigger wave. So now let's look at waves that are perfectly out of phase. So if they're perfectly out of phase, then what will happen is the troughs of one wave, so the trough in wave 2 will align with the crest of wave 1. What will happen then is, because they have the same amplitude, these will cancel each other out basically to form a singular line basically. So destructive interference, we get a wave with an amplitude of 0. And if you have noise cancelling earphones like my AirPods, this is how noise cancelling works. So what happens is the microphones within your earphones, they will start recording the sound around them, and then a chip or a microprocessor or a microchip within your earphones, they'll start processing that audio waves, and then a speaker will start basically outputting a sound wave that runs perfectly out of phase to the sound waves that it's recording. So it will undergo destructive interference to produce 0 sound. So that's how noise cancelling works as well. because if you remember now, the amount of sound or how loud something is directly correlating to the amplitude of the wave, and the pitch or how high the note is directly correlates to the frequency of the wave. That's wave. Those are wave properties that we went through a little bit in year 11 module 2. So that is a quick bit about wave interference and wave diffraction. So now we can move on to Young's double slit experiment. So what is Young's double slit experiment? Well, he did this to see whether light displayed wave or particle properties. And so what he did was he took a light wave and he shone this light wave through two slits very close to one another. So we have a monochromatic wave and it's shot through, or it's directed at a diffraction grating with two slits. And as it hits these two slits, it's creating, so the wave diffracts through these two slits and it creates 2 point source waves. And as it creates 2 point source waves, what happens is these 2 point source waves start radiating out from this point source, and the wave fronts, if you can see over here, they start intersecting, right? And as they intersect, that basically shows wave interaction. So these two slits are really close to one another. That's what you need to know in terms of describing Young's double slit experiment. They're less than a millimeter. So these two slits are very close to one another, but the screen is quite far away from the slit. So it's around a meter away from this slit. So now what we have is a single source of light waves. We shine this monochromatic single source of light wave into these two slits. And then what happens is we get wave interference. So a single source of light waves enters these two slits. Each slit, as I mentioned before, becomes a point source. So now we have two identical but independent sources of light, because the light will diffract the same degree within these two slits. So we'll have two identical but independent point sources of light. And what will happen is, as these two sources of light start, expanding from this given area, as you can see through the intersection of wave fronts, these two waves from the two sources will interfere with one another. And what will happen is, on this screen or on the wall close to it, that's around a meter away, on the next screen that sits really far away from the slits, around a meter away, a interference pattern should be produced of dark and bright spots or bands on the screen. So now think to yourself, why are there dark and bright bands or spots on the screen? Think about what we've learned, or the content that we've learned coming into this. We learned about wave interference and wave diffraction, right? We've already gone through diffraction over here. Now we need to think about wave interference. So what do these white and dark spots mean? Well, these white spot, especially the white spot in the middle, is where the waves undergo constructive interference. So if you look over here, these two wave fronts over here, if they reach this point, what will happen is, it means that at this point over here, it's undergoing constructive interference. So it'll look something like constructive interference. And so what will happen is the wavelengths of these 2 point sources, they will be perfectly aligned. So the crests and the troughs of both of these point sources will perfectly align to form a bigger wave, basically. So it'll undergo constructive interference at this midpoint. Same thing with over here and over here. And so all these light bands will be constructive interference, and similarly all these dark bands, there will be destructive interference. So where these waves are now canceling each other out to different extents and different degrees to form dark bands. So that's what it looks like now. So let's look at the interference pattern in a little bit more detail. So the interference patterns on the screen are caused by the different distances that light travels to each point on the screen. So if they travel the same distance, right? So because they're two identical point sources, they'll have the same wavelength and same amplitude, and by definition, then the same frequency as well. So because they have the same wavelength, same amplitude, if they travel the same distance, then the waves are in phase, right? And so because this is the midpoint, essentially the midpoint between these two slits, they'll travel the same distance to get to these two slits, right? And so they'll be in phase. And if they're in phase, then their crests and troughs align. So we get constructive interference, and constructive interference produces, or we see constructive interference as a bright spot on the screen, because now the amplitude is multiplied, and so we see the white light over as a bright spot on the screen. Now let's say they travel different distances. So let's say they travel different distances. So there are two things that could happen if they travel different distances. So one thing is that wave 2, so the second wave now, so the red wave, wave 2, will travel an extra wavelength, extra one wavelength to get to the second position. So let's look at this second bright spot over here. So this second bright spot on top over here. So for this second bright white spot, what will happen is this bottom point source will have to travel more to get to this second bright spot than the top light wave, right? So wave 2 will travel an extra one wavelength So what will happen is, because it only travels an extra one wavelength, the crests and the troughs will still be in phase, right? They'll still be like connected to one another. There'll still be a one on top of one another. They'll still be in phase. They'll still align with one another. And so the wave will still undergo constructive interference, even though they travel different distances. Because wave 2 is only offset by one wavelength, they'll still be in phase. And so we get a bright spot on the screen, but at less intensity, because technically it's further away from the wave. So because this is technically further away, we get a slightly less bright spot, but it still counts as a bright spot that we see because it undergoes constructive interference. The mid one, or the central maxima, which we'll talk about in a bit, the naming convention. So the central maxima, the mid bright point, will have the greatest intensity. So yeah, central maxima, and then these bright white bands are then called first, second, third maxima, and so on and so forth. But we'll talk about that in a bit. So this is one of the possibilities if the waves travel different distances. The second probability is if they travel an extra half a wavelength. So now we're looking at this bright spot right next to the midpoint. So let's look at this top dark spot, right? This dark spot over here. You can see over here that this point source has to travel less distance than the second point source, right? So they're still traveling different distances, but now we get a dark spot instead of a white spot. Why do we get a dark spot? Well, the dark spot occurs if we travel an extra half wavelength. So if our wave 2 now travels an extra half wavelength, then the waves are out of phase. It'll look something like this. So if it travels an extra half wavelength, then its crests align with its troughs. So the crests are now aligning with the troughs, and so now we get destructive interference. And with destructive interference, that manifests itself as a dark spot on the screen. So now we see destructive interference as a dark spot on the screen, and this occurs so this dark spot on the screen, we call it the minima. So let's go over here. So we call it the minima. So these dark spots or dark bands on the screen are called minima. The bright bands, or the bright white spots, are called the maxima. And this middle point is called the central maxima. This first dark band is called the first minima. This first bright band is called the first maxima, and so on and so forth. Same with down. So this first dark band over here is called the first maxima. This first this white band is called the first maxima, and this first dark band is called the first minima, and this midpoint is called the central maxima. So let's look at how to predict now the location of the maxima, so the bright spots on the pattern, using this formula. So the formula that we use is d sine theta is equal to m lambda. So d sine theta is equal to m lambda, and let's break this equation down. So d is equal to the distance between the two slits. So it's very small, less than a millimeter. Theta is the angle from the center line. Lambda is the wavelength of the light that we're shining. M is the order of the maxima. So the first maxima is found when m is equal to 1. What is the first maxima? Well, let's go back. The first maxima is this first white band. So the first white band is the first maxima, which is this one over here. The first minima is the first black band, which is over here. So m equals 1 is equal to the first maxima, m is equal to 2 is equal to the second maxima, and so on and so forth. So this is how we break down the equation. Now let's solve a question using it. So calculate the angle. So immediately we know that now we're looking for theta. So calculate the angle from the central maximum to the third maxima if 900 nanometer light, so lambda is 900 nanometers, is shown through 2 micrometer slits 4 millimeters apart. So 4 millimeters apart, so that is d. So d is equal to 4 millimeters. 900 nanometers is lambda, and we're trying to find it to the third maxima. So m is equal to 3. So now we have all our data. We can write this out now. So d is equal to 0.004. Lambda is equal to 900 times 10 to the power of negative 9, or 900 nanometers. D sine theta is equal to m lambda, where m is equal to 3. So now we can fill out this equation by going sine theta is equal to m lambda over d. So we can isolate sine theta now, and then we can sub all the values in. So theta is equal to sine inverse m lambda on d. We isolate theta because that's what we're looking for. Then we sub in all the values. So theta is equal to sine inverse of 3 times 900 times 10 to the power of negative 9, or 900 nanometers, divided all by 0.004 to get a value of 3.867 times 10 to the power of negative 2, which is approximately 0.038 which then becomes 0.039 degrees to two significant figures. So that's how you would solve this type of question, and how we would use and practically apply the equation to predict the location of the maxima. D sine theta is equal to m lambda. Now we can similarly find the predicted location of maximas, or the dark spots, using the formula d sine theta is equal to m plus half lambda, because if you remember before, these dark spots or minima are caused when one of the waves are half a wavelength off from the other one. But they don't just have to be half a wavelength, right? They could be 1.5 wavelengths, 2.5 wavelengths, any integer value plus half wavelengths off from, or like different from the other wave. So as long as it's something 0.5 wavelengths difference from the distance traveled, they'll undergo destructive interference. So again now, the distance between the two slits is d. Theta is equal to the angle from the center line. Lambda is equal to the wavelength of the light that we're shining. M is equal to the order of the minima. So the first minima is found when m is equal to a half. So the first minima is found when m is equal to a half. So m is equal to 0 is when the first minima is found. M is equal to 1 is where the second minima is found, and so on and so forth. Now let's look at the resolution of diffraction pattern that we produce. So the more diffraction gratings that we use, so we have double slit diffraction, which is what we looked at for Young's double slit experiment. We have double slit diffraction. The more diffraction patterns that we use, the more resolution that we get. So double slit diffraction looks like this. So we get a single slit envelope over here, and then within that single slit envelope, we see these peaks, right? But if we use a 3 slit diffraction now, within that single slit envelope, we have more resolution and we have more data to work with. And then within a 5 slit diffraction, we have even more resolution and even more data to work with. So as the resolution of a diffraction pattern increases, it's due to the diffraction grating also increasing. All right, so that brings us to the end of our first block. So within our first block now, if I go back to a quick summary of what we did, within our first block, we've covered the development of the model of light. We've also gone through electromagnetic radiation and electromagnetic waves. We looked at Maxwell and all that stuff. And we've also gone through blackbody radiation. Oh, we haven't gone through blackbody radiation yet, but we'll go into blackbody radiation soon, which will segue us into block 2. So this is like a midpoint between block 1 and block 2. With that said now, I think we were on slide 40. Yep, slide 40. Another important thing is, if you guys have any questions whatsoever, I'm present within the live chat. So I'm present within the live chat over on the side of wherever it will be on the website. Make sure to type your questions in, and I'll answer as many of them as I possibly can throughout our 2-hour lecture time limit. So yeah, don't be afraid to ask any questions, because this is new content that you're being exposed to. Don't be afraid if you might think that there's silly questions or not. There are no silly questions. Well, there are, but like I know from personal experience as well that I asked a lot of questions that I would consider stupid when I first started learning this stuff. But that's just like the process of learning, basically. So don't be afraid to ask questions, any questions that you have, and I'll be sure to answer as many of them as I possibly can. So yeah, that is wave behaviors. Now we can get into the quantum model of the light now. So what is the quantum model of light? So right now we've gone through the wave model of light, the particle model of light, and we know that the wave model of light overtook the particle model of light. So a quick bit about why the wave model overtook the corpuscular model, or why the corpuscular model of light was discarded. Remember, the corpuscular model is the particle model. So why was the corpuscular model of light discarded? Well, if you think back to what corpuscles were, Newton said that corpuscles were particles that were attracted to a mass, right? So technically now, if light entered a more dense medium, then you'd think that light would speed up, right? Because if these corpuscles, which make up like light, are attracted to mass, then a more dense medium would have more mass, right? It would have more mass, more particles with mass. So then that light wave, or this corpuscle, should speed up, right? Well, that's what Newton's model predicted. Well, Huygens' model was the opposite. The wave model predicted that it would slow down. So what did was, so Foucault, if you think back, Foucault with his rotating mirror contraption, which was the fourth guy that we talked about for historical models of light, what Foucault did was he tested this theory by then basically measured the time taken for light to travel through air and then light to travel through water for a certain distance. And what he found that light would take a longer time to travel through water than to travel through air. So that provided experimental evidence that supported Huygens' model of wave model of light, because it showed that light didn't in fact speed up when it entered a more dense medium. And so that was experimental evidence that was favoring Huygens' model, and it was not favoring the corpuscle model. And the important thing to realize is, as scientists, we use experimental evidence to develop and further improve our current models. So that's what we do as scientists. So experimental evidence is what leads us to improve on our models and gain more accurate representations of what we see or phenomena that we see in real life, right? So another important thing is, when we did Young's double slit experiment, so Young's double slit experiment showed, what did it show? The interference pattern, it showed proof of wave interference. So light showed wave properties of interference, right? And interference was displayed by the bright white bands that you could see on the screen. So these bright white bands was proof that light could undergo interference and diffraction. What are diffraction and interference? They're strictly wave properties. So this experiment, once again, was supportive of Huygens wave model of light, and so the wave model of light, due to the large amount of experimental evidence that was supporting it, became more accepted than Newton's particle model of light, or the corpuscular model of light. So that's what ended up happening. But now we have moved on from even the wave model of light to the quantum model of light, which was made by Einstein. So what are the features of the quantum model of light? Well, it states that light consists of small discrete energy packets called photons. So we're now back to this idea of it's made up of small things called photons. So that is one of them. And if you see over here, photons are in red. So you should be able to define what a photon is. Well, photons are small discrete energy packets, as per what this dot point says. And you should be able to, at least understand the concept of a photon. So basically, the photon model or the quantum or photon model of light also stated that the energy in each photon is related to the frequency of the light. So frequency now dictates energy, or frequency of light dictates the amount of energy it carries instead of intensity. So the wave model linked it to intensity. So the intensity of light would be related to frequency. The quantum model stated that the energy is equal to the frequency. So frequency is directly relating to energy, and we'll find out an equation to map that out, to look at that relationship. So what else did it say? Well, it said that the intensity or amplitude of the light wave is related to the number of photons. So instead of it being equal to the frequency, now it's equal to the amplitude, and dictates the number of photons. So the greater number of photons that I shoot out, the greater the number of the higher the intensity of the light wave that I shoot out. So that's kind of what that dictates. And the other important thing about photons is, this can help you answer help you with a flowchart that you'll write about photons maybe. So photons are a type of fundamental particles. Well, what are fundamental particles? So fundamental particles are, for example, particles that are even less than protons and neutrons. So they're like electrons. Electrons can't be broken down any further. Protons and neutrons, they can be broken down further into even smaller particles, which we'll learn about in module 8. But basically, photons are even smaller than their fundamental particles. So these fundamental particles, they just cannot be broken down any further. They are the building blocks of the universe, basically. So protons and neutrons, they aren't fundamental particles because they can be broken down further into quarks, which are fundamental particles. And you learn about the different types of quarks in module 8. But for now, all you need to know is that photons are fundamental particles as well. And so they cannot be divided at all. And so if these photons can't be divided, then if I absorb light, that means I have to absorb a integer value of photons, because I can't absorb 1.5 photons, right? Because I can't divide a photon into two things. I can't divide a photon into 0.5 and 0.5. I have to either absorb the entire photon, or I have to not absorb the entire photon, or I have to just not absorb it at all. So I have to absorb it all or nothing. So that's what the all or nothing principle is about. So these are a couple dot points about the features of the quantum or photon model of light. And so now we can move on to the blackbody radiation. So how did the photon model of light come across? Well, the photon model of light was motivated by several failures of the wave model of classical physics, where predictions made by the model didn't match. So wave model of classical physics didn't really match our expectations or observed expectations, even though it came across, it was better than the corpuscular model, but it was still not as good as it was not what we needed, because it didn't explain all the phenomena that we saw light displaying. So the two things that that the classical physics model to the wave model failed to explain or failed to account for is known as the ultraviolet catastrophe and the photoelectric effect. So we'll go through this in detail, and you will be tested on the photoelectric effect, especially. The ultraviolet catastrophe is more of like a content dot point, but the photoelectric effect, they can ask you questions on it, so like calculation questions. So, but before that, let's go into the concept of a black body. So what is a black body? And you need to know what a black body is because it's in red now. A black body is a perfect absorber and emitter of electromagnetic radiation. So nothing is reflected from a black body. It is only absorbed and then re-emitted. So no light wave or no wavelength of electromagnetic waves is reflected. It is absorbed and then re-emitted. So the thing with black bodies are they're only theoretical. So there is like nothing that perfectly absorbs and re-emits something. Stars are a good approximation of black bodies. Black bodies, they emit radiation across the electromagnetic spectrum, and we can graph these as what we know now is the black body radiation curve. And I'll show you what that looks like. It looks something like this image over here. This is what it looks like, a black body radiation curve. So the x-axis of the black body radiation curve shows the wavelength of radiation, and the y-axis shows intensity. Well, the units for intensity are arbitrary, so they could give you like a massive confusing unit for intensity. Doesn't really matter. The x-axis, we should know it to be wavelength, and using this, we can calculate the temperature of an object. So there's an equation that denotes the relationship between temperature and wavelength. So let's go through this. Let's go through the ultraviolet catastrophe before that though. So what happens is the scientists used the wave model of light to predict blackbody radiation curves. So they tried to use our wave. So currently now, but we haven't. So in time currently, so within our journey right now, we haven't entered the quantum model of light period yet. We're still in the wave model of light era. So now, within the wave model of light era, what scientists did was they tried to use the wave model to explain or to predict what a blackbody radiation curve might look like. So this 5000 Kelvin shows the blackbody radiation curve for an object of 5000 degrees Kelvin. So this is what it actually looks like. But what does the wave model or the classical model of light predict? Well, it predicted that like it would go up to so it would just keep like increasing and increasing, and it would asymptote at zero basically. So what it said was the problem with this is that it said that as the wavelength. So if you look at this graph for classical theory, the black line over here, this graph basically indicated or told scientists that as the wavelength of electromagnetic radiation emitted becomes closer and closer and closer to zero, the intensity of that light wave would approach infinity. And that obviously violates the law of conservation of energy because we can't have infinite energy in something. So that was an ultraviolet catastrophe. And then, that was so perplexing and mind-blowing at the time because scientists thought at that time that the classical model of light could explain all the phenomena about light or all the phenomena displayed by electromagnetic radiation. So this ultraviolet catastrophe is very shocking at the time. So what are the problems? So there's two problems. One is that classical theory didn't match these observed curves, so we couldn't map it to the curves, and we couldn't map it to the observed values. The second thought was that classical theory thought that energy would increase exponentially with frequency, and so it suggests infinite energy because as the wavelength decreases and thereby frequency increases, so as this happens, infinite energy would be generated. So as the wavelength decreases as the wavelength approaches zero, it basically predicted that the intensity of the light would reach infinity, so it would carry infinite energy. So this violates the law of conservation of energy, which states that energy can neither be created nor destroyed. And so this failure for classical theory to match the predictions of predicted observations, experimentally observed observations, became known as the ultraviolet catastrophe. So now we learn about a dude called Max Planck, and he is the guy who came up with he's the guy who helped Einstein come up with the quantum model of light. And Einstein basically used the equations that Max Planck gave to create the photons, basically, or create this or map or create the relationship between energy and frequency. So what Max Planck did was he came up with a mathematical trick to fix or remedy the ultraviolet catastrophe. So what he did was he considered the radiation or the wavelengths or the light waves or light or EM radiation emitted by a black body to be emitted in discrete packets called quantas. And so what happened was the energy of these quanta was attached to frequency. So E is equal to HF, energy is equal to Planck's constant times frequency. And so this is the relationship between energy and frequency. And we'll revisit how to use this and how to apply this in more detail in module 8. But for now, E equals HF if what we know. So h is equal to 6.626 times 10 to the power of negative 34. This is known as Planck's constant. It's on your data sheet. And so this is the equation that he came up with. So now if we go to the photon model of light, the energy in each photon is related to the frequency of light. So if we're trying to find the energy in a photon of light carrying, let's say 300 hertz, what we do is a photon or a quanta of energy. So a photon, which is a quanta of energy, a photon, like basically, let's just say light or electromagnetic radiation with a frequency of 300 hertz would have a photon carrying 300 times. So 300 hertz times Planck's constant, which is 6.626 times 10 to the power of negative 34. It would carry 1.9878 times 10 to the power of negative 31 joules of energy. So that's what it would look like. And so this is how you would calculate the energy within each photon. And so now we can do what I did before, where I said we can use the blackbody radiation curve to find the temperature of an object, and that's called through Wien's law. So what Wien's law did was he used the location of the peaks on these blackbody radiation curves to map temperature. And let's think about this logically, right? So if you think back to 2016 or back in the day, basically, the 1,000 degree like knife cutting thing was a thing, right? So they'd use a 1,000-degree knife to cut through so many different objects, major clickbait on YouTube and stuff. But if you look at all their thumbnails, it's like an orange glowy knife, right? Normally knives don't glow like that, but they're now glowing orange. And what is the color orange? It's a form of electromagnetic wave, right? So it's an electromagnetic wave with a specific wavelength of, let me quickly look that up. What wavelength is orange light? What wavelength is orange light? Orange light has a wavelength of 600 nanometers. So basically, these 1,000-degree glowing knife, these 1,000-degree glowing knives, not 1,000 degrees, but these glowing knives that were glowing orange would be emitting electromagnetic radiation of 600 nanometers to into our eyes, right? So we'd absorb these electromagnetic radiation of 600 nanometers, and we'd process it as the color orange. So that's what that would look like. And so we can now use that electromagnetic radiation on the wavelength of that electromagnetic radiation emitted to calculate the temperature of that knife. So if it was emitting an orange color, right, we could say now that this, but obviously we need to understand that the metal in a knife is not a perfect black body. So they can have a lot of inaccuracy. But the thing is, if the wavelength is, around 600 nanometers, we can now use Wien's law, which is the peak intensity is equal to B over T, right? So B is Wien's constant over temperature in Kelvin. So if it emits an orange color, if we process it as an orange color, that means it's emitting a wave of 600 intensity, a light of a wavelength 600 intensity. Sorry, let me just restart that. If we are now seeing the knife glow orange, what it means is it is emitting a light wave of 600 nanometers wavelength at its maximum intensity, because we'll see the color of maximum intensity as the color that we'll process, right? Because if it's emitting the color blue at a very low intensity, then we'll see the orange color over the blue color, right? So we'll see the orange color, which means the wavelength of maximum intensity being released is the orange, which is 600 nanometers. So we have to, if I'm now calculating the temperature of the knife, I have 600 times 10 to the power of negative 9, which is equal to the wavelength, and I divide Wien's constant by that. So I do 2.898 times 10 to the power of negative 3 divided by 600 times 10 to the power of negative 9 to get a value of 4,830 Kelvin, which is a lot more than 1,000 degrees. It's probably 4,000, it's very high basically. So that's how we would calculate the temperature of that knife, assuming that that knife or the metal within that knife, the material of that knife, was a perfect black body. So we can use this, like Wien's law now, to calculate or approximate the temperature of a star, because stars also emit colors, right? Stars are basically a good approximation for black bodies. Stars emit a certain wavelength of light, which is why we see our star as orange or yellow sometimes. So we can use this to calculate the temperature of stars. So let's look at, instead of stars now, we have a black body cavity. So this is a black body now. So we can now use the black body radiation curve to find the temperature of this black body. So what we do is we first now find the wavelength of maximum intensity. What is the wavelength of maximum intensity? It occurs somewhere around here, right? It occurs somewhere around here. So we have the maximum intensity. We can now trace it downwards to where it is within the graph, and we'll find that wavelength emitted at maximum intensity. and we'll use Wien's law to calculate the temperature, just like how I did earlier. So it would look something like this. So what is the maximum wavelength, or the wavelength of maximum intensity? It is 490 nanometers, like, give or take a few nanometers, but yeah, approximately 490. So now we use the equation lambda max is equal to B over T. I rearranged that to isolate T because T is what we're looking for. So T is equal to B over lambda max, and then I sub everything in. So 2.898 times 10 to the power of -3, which is Wien's constant, divided by our wavelength. So lambda max, which is equal to 490 times 10 to the power of -9, to get a value of 5.9 times 10 to the power of 3 Kelvin, approximately, which is our answer A over here. So that's how we would do this blackbody radiation question. All right, so now let's look at the photoelectric effect, which is, so we looked at now the ultraviolet catastrophe, which is one area where the light model couldn't keep up with. Now let's look at the photoelectric effect. So another unsolved problem of the 19th, 20th century was the photoelectric effect. So this was another failure of the classical theory of light, or the wave model of light. So this is an experimental setup to show the photoelectric effect. So what we do is, I'll go through the different parts now. So this is what it looks like. We have a light wave hitting the metal surface, and as that light wave hits a metal surface, it'll emit an electron. So as the photon, or like, it comes photoelectric effect because as a photon strikes the metal surface, an electron is emitted, or as a light wave hits a metal surface with a certain intensity, obviously, an electron is emitted, and we detect that electron using the ammeter, which will show that there's current within the coil, or there's current within the circuit, right? So we have a detector. The electron now travels like this, causing the ammeter to detect a current as the electron is moving. And yeah, that's kind of what the photoelectric effect looks like. So photoelectric effect is the phenomena where, as a light of specific intensity it hits a metal surface, an electron from that metal surface is emitted. That's basically what the photoelectric effect is. And if you see over here, the photoelectric effect is in red, so you should be able to define it. All right, so let's look at the photoelectric effect now. So expectation versus reality. So now let's look at the expectations, which is, what the wave model would say about the photoelectric effect. So what it said was, what the wave model said was, light of greater intensity would emit higher energy electrons. So this is all like phenomena, or like predicted phenomena based on what the wave model said. And then we'll look at the observed phenomena, or the experimental data based on, like, what we actually observed experimentally. And these would all align with what the particle model would say. So what did the wave model say? It said that light of greater intensity would emit higher energy electrons. This turned out to be false. And another thing that it would said was, as we expose the metal to light for longer, we would allow the energy to build up in electrons. So if we would shine light of very low intensity, the wave model said that as long as we keep shining on it for a long enough time, we would build up energy within the electrons until it had enough to escape. This also turned out to be false because, if we think back to our concept of photons being fundamental particles, if they don't have enough energy to, be absorbed into the electron to cause the electron to leave, then it just won't work, right? Because it can't absorb. It's an all or nothing principle, right? It can't absorb parts of the photons to keep making the electron leave. It either absorbs everything and it doesn't leave, or it doesn't absorb it at all and it doesn't leave as well. So the next part is that energy of emitted electrons would be dependent on the intensity of light. This was also false because if we think about the photon model, right, the intensity is dictated by the number of the photons. So if I shoot like 10 times the number of photons that I did originally, so I increased the intensity by a factor of 10, but all these photons didn't carry enough energy to make electrons leave, then I would still emit no electrons from the metal, right? So there'd still be no photoelectric effect observed. So the way it works is this light supplies energy to this metal, so it supplies energy to the electrons, like the flame test that we did in module 1, right? So it would excite these electrons, causing them to leave the metal surface. Basically, that's how that works. So let's look at reality now. So light of greater intensity doesn't affect electron energy. What it does is it increases the current. Why? Because if we think back to, it increases the current caused by, and this is what we determined, and this is what we saw experimentally. So now let's try to explain it using the particle model of light. Well, why would it increase the current? Well, if we think back to what the particle model said, we linked intensity to number of photons, right? So if we shoot a greater number of photons, then assuming that all these photons are above the threshold or they have enough energy within them to cause the electrons to leave, then if we increase intensity, we'll cause more electrons to be emitted. And if we emit more electrons, then within that coil, there'll be more electrons. So the current would be greater, right? So there'll be more charge traveling through the same amount of time. So the current would increase as you would increase intensity. the energy or the kinetic energy of these electrons would not increase. So photocurrent would increase, photovoltage would not increase. Then we'll look at the next point, which is what we said was, we said that if we expose the metal for light long enough, we would build up energy in the electrons so that they would escape eventually. Well, that's false as well, because the emission of electrons was always instantaneous from the moment light struck the metal. So it was either the photon wasn't absorbed at all because it didn't have enough energy for it to leave, or the photon did have enough energy for the electron to leave, so it was fully absorbed. So no matter how long we shoot out photons, if all these photons don't have enough energy for the electron to leave, then none of them will be absorbed, following the all or nothing principle. So we're doing nothing basically. So exposing the metal to light does not allow the energy to build up. It's an instantaneous process. Either the energy is fully absorbed instantaneously and the electron leaves, or it's not absorbed at all and the photon just bounces off basically. And then the next part, which says the energy of emitted electrons would be dependent on the intensity of light. Well, it's not dependent on the intensity of light, it's dependent on the frequency of light, following E equals hf, following Planck's equation. The energy of the emitted electrons was determined by the frequency of light, right? This is what we did earlier as well. So that is what the reality was, and the reality fitted the particle model of light, or the photon model of light. Hence, the photon model of light became accepted. So in terms of explaining reality, what happens is light hits the metal as photons. So these photons, they hit the metal and they carry packets of energy, right? These packets of energy are determined by E equals hf. So the amount of energy within each packet would be determined by hf, following the equation E equals hf. And the size of this energy packet is dependent on the light's frequency, right? So that's following E equals hf again. So what happens is each electron absorbs this energy from one photon, and if it absorbs this energy from one photon, then we now understand that that photon has enough energy for the electron to leave. So what we know is within each metal, a certain amount of energy is required to free the electrons, and this is different for every metal. So every metal has a threshold, or an energy threshold, that the electrons have to surpass to leave the metal. So this is unique. And so if an electron absorbs the energy from a photon, that means the photon has enough energy to make this electron leave. So it has enough energy for the electron to overcome this threshold. And as it overcomes this threshold, the excess energy so if a photon has more than enough energy for it to leave the metal, then this extra energy is converted into the electron's kinetic energy, or it is converted into the electron's speed. So the greater the energy of the photon, assuming that it's above the threshold, the greater the speed of the electron as well, following kinetic energy, K E is equal to half mv squared. So that's how that process works. What happens if the photon doesn't have enough energy? Well, the photon, it just doesn't get absorbed. So it would hit the electron, nothing would happen, because the energy supplied wouldn't be enough for the electron to leave the metal. So it would try to make the electron leave, but not enough energy for the electron to leave, so nothing would happen. And so the electrons would get excited and they would just return back onto ground state afterwards by releasing an electromagnetic radiation right after that. So it's basically like exciting the electrons, but we're not exciting it enough for the electrons to leave. So now we can think about the threshold. So I mentioned that every metal has a certain amount of energy required to free it from the metal, right? Required for the electrons to be freed. What is that called? Well, it's called the threshold frequency, or the work function, basically. So the kinetic energy of emitted photoelectrons is dependent on the energy of the photon it absorbs and the amount of energy it takes to break the electron free. So if we're now trying to express this last dot point within an equation, we get the kinetic energy of the photon emitted is equal to the kinetic energy that we supply from a photon minus the work function of the metal. What is the work function of the metal? It is basically the amount of energy, or like the threshold energy that is required to free it from the metal. So we minus the energy that we supply from the photons. So we minus the work function of the metal from the energy we supply from the photon to find out the excess energy, and that excess energy is then what we have as kinetic energy. So what happens if the supplied energy is equal to the work function? Well, we give the electron enough energy to leave the metal, but it's going to leave the metal with a velocity of zero, right? Because after it leaves the metal, the kinetic energy will be zero. So the electron kind of just like hangs around at the end of the metal. It doesn't leave the metal with a velocity because our excess energy is equal to zero. So what do we call the minimum frequency required to overcome the work function? We call it the threshold frequency, because the work function is also determined by Planck's equation, hf. And this F that we use to calculate the work function is called by threshold frequency. So, but don't confuse this HF with the HF above over here, because this HF is corresponding to the energy within a photon, and this HF is corresponding to the frequency that we need to supply to overcome the work function of the metal. So now let's go through a couple questions. So we're using this equation. What we do is calculate the energy carried by so we don't use the equation over here. What we do is we put into application our understanding of Planck's equation. So calculate the energy carried by a photon from a light of frequency 300 gigahertz. So if I have frequency 300 gigahertz, how much energy do I have? Well, I follow E equals HF. So I do E equals HF, which is equal to 6.626 times 10 to the power of negative 34, following Planck's constant. And we multiply that by times 300 gigahertz, which is 300 times 10 to the power of negative 9, to get a value for energy of 1.9878 times 10 to the power of negative 22 joules. So that's what that would look like. Now let's calculate the wavelength of a photon that carries 3.976 times 10 to the power of negative 19 joules of energy. So how do I do that? Well, I write down E equals HF again, and now I change F into C over lambda, because C, which is the speed of light, is equal to F lambda. So if I rearrange this equation, I get F is equal to C on lambda, and I can sub that into this equation to get E is equal to HC on lambda. Then I isolate lambda because that's what I'm trying to find. So I get lambda is equal to HC on E, and then I sub in all my values. So I get 6.626 times 10 to the power of negative 34 times 3 times 10 to the power of 8. So 10 times 10 to the power of negative 34 times 3 times 10 to the power of 8 divided by E. What is E? Well, we have E over here. The amount of energy it carries is 3.976 times 10 to the power of negative 19. So 3.976 times 10 to the power of negative 19 to get a value of around 4.999 times 10 to the power of negative 7 meters. So that's approximately 5.0 times 10 to the power of negative 7 meters to two significant figures. So that's how I would answer these two types of questions. All right, so now let's go to the photoelectric. Let's go through the photoelectric effect questions. So a beam of monochromatic light strikes a piece of aluminum in a vacuum chamber, as shown in the diagram below. So this is the apparatus for the photoelectric effect. What does the frequency of this light need to be so that the current will flow in the circuit? So we need the minimum. So we're basically trying to find the minimum energy for the current to flow through the circuit. So the work function of the aluminium is 6.54 times 10 to the power of negative 19. So what are we looking for? Well, we're looking for threshold frequency. So let's calculate threshold frequency now. So because that is the minimum amount of energy needed for current to flow in the circuit, right? So the threshold frequency is HF is equal to this equation over here, or this symbol over here. So F is equal to work function divided by H, which is equal to, what is the work function? Work function is 6.54 times 10 to the power of negative 19. What is H? H is 6.626 times 10 to the power of negative 34. Get a value of 9.8702 times 10 to the power of 14, which is approximately 9.9 times 10 to the power of 14 hertz. So that is the amount of frequency we need to supply for a photocurrent to be observed within that circuit. All right, so now let's go through spectral analysis. So we're nearing our second last topic in module 7. So yeah, we've gone through a lot of content. So there is a lot of content that you need to go through for module 7. It's pretty chunky, which is what I said in the beginning. Module 8 gets a little bit more chunky as well, but if you think of it all as a story, if you think of it all as like, a journey across time, basically, then it gets a lot easier. So we're looking at two journeys, right? One journey is the development, or one journey is like the historical methods of finding the speed of light. So it's a journey from Galileo to old Roma to Fitzo and Foucault. So these four guys, there was a journey on how to calculate the speed of light, and then we go through a second journey, which is trying to explain the properties of the speed of light. So we get to the photon model at the end, and using the photon model now, we can use it to study. So this is the applications of the photon model. We can study properties of matter based on how it interacts with EM radiation. And this basis of study is called spectroscopy. So spectral analysis, now what can we do? We can do two things. So one thing that we can do is we can detect the frequencies of radiation absorbed when light is bounced off or shown through a substance. And this is called the absorption spectrum. So we can find the wavelengths or frequencies of light that is absorbed by a substance when we shine light through it or light onto it. The next thing that we can do is we can excite the substance. One way we can excite the substance is by basically supplying it energy. We can do that by heating it up, for example. And then by supplying it energy, we can detect the frequencies of radiation emitted by the substance as it relaxes. So we excite the substance, so we give it energy, and then as it relaxes, it releases energy in the form of photons, or in the form of light. And we know now that light carries energy because we're using the formula E equals HF. So it will release the energy that it absorbed via like wavelengths of light that would, that follows the equation E equals HF. So this is known as the emission spectrum. So the emission spectrum is like this. So basically colorful bands across a dark spectrum, because this shows the discrete wavelengths emitted by a substance as it relaxes. And then the absorption spectrum shows is a dark bands following a rainbow gradient of a rainbow gradient band, and we have dark bands or dark slits across that band, and that shows the discrete wavelengths of light that they absorb. So that's the two things, the emission spectra and the absorption spectra. And using these now, we can calculate properties of stars. So we can calculate property of stars, for example, temperature. So using the peak of the radiation curve, or the peak of the blackbody radiation curve, we can indicate the temperature of the star, and we can use the concept of the theory. So this is Wien's law, basically. Wien's law in application is for spectral analysis. We can calculate the temperature of a star. What else can we, and this is kind of what the spectra of a star will look like. Now, if you look over here, these dips that can be seen as, the absorption spectrum. So these dips will indicate the discrete elements that the star will be made up of. And so, yeah. The next thing that we can do is we can calculate the chemical composition of these stars. So the position of the spectral lines, because every element will require a discrete amount of energy to be excited, and so they will release a discrete amount of energy after excitation when they go into relaxation. Because these elements have unique spectral lines, then because they release unique and discrete amounts of energy, we can use these spectral lines to calculate the different elements within that star. So that's another practical application of spectrum of the photon model of light, or our understanding of light as photons. So we can calculate the chemical composition of stars. What else can we do? We can calculate the translational velocity. Translational velocity is basically calculating, is the star moving towards us or is the star moving away from us? So this is a application of Doppler's effect, which we also did in year 11. So it's like another wave property, basically. So if a star is moving towards us or moving away from us, the spectral lines of the star will be shifted. So if the star is moving away from us, thinking back to the Doppler effect, right? So the light source is traveling towards us, but the source of light is traveling away from us. So the light wave is traveling towards us, the source of light is moving away from us, then that light wave is going to get stretched, and so it will become redshifted. So we can see this is what would happen if it's stationary, and if it's redshifted, the entire spectra basically gets shifted a little bit to the left, but we can still find the chemical composition because the patterns of the absorption and emission lines will be the same. What happens if the star is moving towards us? Well, the light wave is traveling towards us, the source of energy is also traveling towards us, so the source of light is also traveling towards us, so now the light gets squished. So the wavelengths become shorter, and so it becomes blue shifted. So it travels more towards the blue end of the spectrum. So this is what would happen if it was stationary. This is what it would look like if it's red shifted. And then the bottom over here is what it would look like if it was blue shifted. So that is translational velocity. We can also go through rotational velocity. Well, what is rotational velocity? Well, rotational velocity indicates to us whether a star is, or how much, or the degree, or like the intensity of rotation of a star, right? Because if the star is rotating, one end of the star is going to be moving towards us, as the other end is going to be moving away from us, because it's rotating like this, right? So if you look at the diagram, as it's rotating counterclockwise, what will happen is this end over here is moving towards us, this end is moving away from us, and so this end, the light waves are going to be, or the wavelengths are going to be shorter, they're going to be squished, and at this end, the light waves are going to be stretched out. So what will happen is the spectral lines, so this is also an application of Doppler's effect, so what will happen is the spectral lines will have a greater width, so they'll get basically pulled apart more. So the width of the spectral lines are proportional to rotational velocity. So that is rotational velocity. The next thing that we can do is we can also find the density of stars. So how do we find the density of stars? Well, denser stars have more blurred spectral lines, and there's also something called pressure broadening, where the spectral lines will also be broader. So if there's pressure broadening, right, so if the spectral lines are broader for both density and rotational velocity, how do we differentiate between the two? Well, rotational velocity doesn't have blurry spectral lines. So if the spectral lines are quite blurred, and we see broadening, so it's indicative of pressure broadening, then what we see is the density of the star is what we're looking at. So the density of the star is greater. If we only see wider spectral lines, that means we're looking at rotational velocity instead of the density of the star. So this is due to more uncertainty in the interaction between atoms and their energy changes. That's why we have blurred spectral lines, due to the more degree of uncertainty. Let's go through a question now. So we have these three spectrums. Let's go through the question now. Let's look at, or like, let's compare the differences between these things, right? So let's have these three questions. So we have diagram 1, which is the stationary light source or stationary source of things shined through hydrogen, right? So this is what we have over here, or a stationary, so hydrogen emits these emission spectra. So this is the emission spectra of a stationary vial of hydrogen, basically. This is the emission spectra of star Croesus. This is the emission spectra of star Dromis. So let's look at all the properties. Let's describe all the properties of each thing. So can we find temperature? Well, we can't find temperature for these because we don't have the blackbody radiation curve, because we need that to find temperature. What can we find? Well, we can find the chemical composition, right? If you look now at the pattern of the elements, so the pattern of the bands in the spectrum for hydrogen in diagram 1, we can see that this pattern is emulated in diagram 2 and diagram 3. Although diagram 2 is more towards the right and diagram 3 is wider and a little bit towards the left, they have the same pattern. What does that mean? Well, if they have the same spectral lines, so the same general pattern of spectral lines, that tells us that the composition of all three stars are the same. So what that tells us is the composition of star Croesus and star Dromis are the same. So star Croesus, same with hydrogen. So star Croesus and star Dromis are made up of hydrogen. So that's what it tells us, because the patterns of spectral lines are the same. So that's one thing. So if I'm answering this question, I'll do one subheading saying chemical composition, and I'll explain that the chemical compositions are hydrogen because they have the same spectral lines with different shifting, basically. So that segues us onto translational velocity. So translational velocity, right? Let's look at this pattern. So in diagram 2, it has the same pattern, but it's shifted towards the right, right? So it's shifted this entire spectral lines, they're all shifted towards the right slightly. What does that mean? Well, if we go back to translation velocity, if it's shifted more towards the right, then it's going to be red shifted. It's more shifted towards the red end of the spectrum, right? If it's shifted towards the red end of the spectrum, what does that mean? It means that the star is moving away from us, right? Because it has to, as the light waves are coming towards us, star Croesus is moving away from us, so the wavelengths get stretched out, and so it appears more on the red side of the spectrum. So we can now say that star Croesus has a different translational velocity to star Dromis, as star Croesus is moving away from us. Why does it have a different translational velocity to star Dromis? Well, if you look at star Dromis, it is slightly blue shifted, right? Because it's shifted slightly to the left. So it's shifted slightly to the left end of the spectrum. So it's blue shifted, which means star Dromis is moving towards us. So we can say now, so our next subheading will be translational velocity, and we can say, although star Croesus and star Dromis share the same chemical composition, they have opposite translational velocities. Star Croesus has a spectrum that is slightly shifted towards the red end of the spectrum, and then in brackets, thus red shifted. And so star Croesus, following the Doppler effect, is moving away from Earth. In contrast, star Dromis is blue shifted, indicating that it's moving towards the Earth. So that's a difference as well. What's another thing that I can see? Well, if I look over here, it's quite blurry, right? And what does this blurry indicate? Well, it indicates the density of the star. So denser stars have more blurred spectral lines. So let's compare the blurriness of diagram 2 to diagram 3. Diagram 3 is a lot more blurry than diagram 2. What does that mean? It means star Dromis is a lot more blurry than star Croesus. Or star Dromis, is a lot more dense than star Croesus. So the next subheading that we'll write is density. I will say, due to very evident blurring of spectral lines in diagram 3, and due to the lack of blurry spectral lines in diagram 2, it's evident that star Dromis is a lot denser than star Croesus. So that's another difference and another comparison that we can make using the data that they've given us. What else? Well, we can't really talk about rotational velocity because, the width of the spectral lines are quite similar. So we've talked about basically everything that we can extract from our understanding of spectras. So that's how you would answer a question like these. Make sure to give subheadings so that your answer is a lot more neat and a lot more efficiently structured, basically. So yeah, that is how you would answer a question like this. Again, if you guys have any questions with what we've learned so far, then make sure to drop a question down in the online live Q&A section. But yeah, now let's move forward. So Let's look at special relativity now, our final dot point, and be prepared for this, guys, because it's gonna kind of bend your minds. It's gonna break your mind. So be prepared for this. So in 1905, Einstein proposed two postulates, which have insanely strange results for time and space, or our current understanding of time and space. So he said that the speed of light is an absolute constant, the same in all reference frames. So what it said was basically if it's the same in all reference frames, and it's also said that inertial frames of reference are equivalent. So let's look at the first one. The speed of light is an absolute constant, the same in all reference frames, right? So this was partly derived from James Clerk Maxwell, right? And scientists were already studying experiments from experimental results, but also if you think back to Maxwell, right? What he did was Maxwell discovered that he calculated light through two constants. And if they're two constants, then, constants are always constant, right? So if light is produced using two constants, that means the speed of light is also a constant, right? So it kind of hinted towards that. And so this is pretty supportive evidence of the speed of light being an absolute constant. And so what does this mean to us? Well, think about us traveling at the speed of 0.9 c. So 0.9 c is 0.9 times the speed of light. So I'm in a train now, or I'm in a box traveling at 0.9 c. I can't see the outside, all the walls are covered in. I'm just in a white cube, inside a white cube, a hollow white cube traveling at 0.9 c. And I shine my torch. So what does this mean? Well, I'm not going to see the torch travel at 0.1 c, right? I'm going to see the torch travel at c. I'm going to see the torch at 3 times 10 to the power 8 meters per second, even though I'm technically traveling at 0.9 c, I'm going to see light traveling at 1 c. So if I'm now looking from an outside perspective, you'd think that that light will be traveling at 1.9 times the speed of light, because I'm traveling at 0.9 and I'm shining a ray of light at 1 c, but it's not. So from inside the box, I see light traveling at c, even though regardless of what speed I'm traveling at. So even though I'm traveling at 0.9 c, I see light traveling at 1 c. And from outside the box, if I could now see the inside the box from outside the box from a stationary perspective, I still see light traveling at 1 c. So that's kind of what is trippy. So no matter which perspective I'm looking at it from, light will always travel at 1 c. So that's where the trippiness comes from. So even though light is traveling at 1 c from inside a box that's traveling at 0.9 c, if I'm looking at it from the outside, light will be still traveling at the speed of 1 c. So the next one says that all inertial frames of reference are equivalent. And so what does inertial mean? It means that inertial frames of reference relates to frames of reference that are non-accelerating, so they travel at a constant velocity that includes 0 meters per second. So it includes us being at rest. So basically, an inertial frame of reference is a frame of reference that is moving at a constant velocity, so no acceleration occurs. So what is this saying is, so what this idea of inertial frames of reference are saying is, if I'm in a room that's boxed in, so let's say I'm back in this hollow white cube, I'm unable to see the outside world, right? I technically wouldn't know what speed I was going at. If I'm at a constant velocity, I could be going at 10 times or 10,000 kilometers per second, or I could be going at 0 kilometers per second. I wouldn't be able to tell because there's no acceleration, so I'll feel no force. I'd be going at a constant velocity, and I wouldn't be able to tell what speed I was going at. The important thing here is because I wouldn't be able to tell, that basically says that all of Newton's laws, so Newton's first, second, and third laws, hold up within an inertial frame of reference. So even if I was at rest or if I was traveling at a constant speed of light, all of Newton's laws would still hold up. That is Einstein's second postulate. So why is this that much of a big deal? Well, let's consider the train thought experiment, right? So a light clock. So let's take a light clock now. 1 tick is equal to the time taken for a beam of light to bounce back. So let's look at this light clock over here. So 1 tick is the time taken for light to start from the source, hit a mirror, and then bounce back to the sensor. So that's 1 tick. So now let's place this light clock in a train moving at a high speed, right? So what does this mean for us? Well, what does this mean for us? Well, if I'm looking at it from inside the train, then I see it as just like this, right? I see it going up and then coming back down. So 2 straight lines. What if now I am looking at it from outside the train? Well, I see it So as instead of me seeing it go straight down, because the train is also traveling, I see it going at an angle, right? So I see the path of light going at an angle to reach the sensor, and then I see it going at an angle back up again to reach the light source, or to reach the second sensor, right? So I see now light traveling at a triangle instead of I see light now traveling at a triangle instead of two straight lines, right? So this is where the trippiness comes in. The thing here is that even though I see it traveling like a triangle, even though I see it traveling at a triangle, and I see from inside the train I see it traveling at a straight line, this all happens within the same time frame technically, right? So if I'm outside the train, I see light traveling a greater distance, but if I'm inside the train, I see light traveling a smaller distance, even though it all happens within the same time frame. What does this mean? Well, it would kind of mean that if I'm outside the train, I see light traveling at a faster distance than if I'm inside the train, right? But that breaks Einstein's first, so the observer outside the train now sees light traveling at a greater distance than the observer inside the train. So if speed is equal to distance over time, that would kind of indicate that I would see light traveling at a greater speed if I was outside the train compared to if I was inside the train. But Einstein's first postulate stated that the speed of light is always constant, right? He stated that the speed of light is always constant. So what does that mean for us? Well, it means that this thought experiment just cannot be the case, right? So what we now have is a process called time dilation. So let's try and rectify this. So Einstein said that the speed of light always stays constant, but if we go through what we observed, it would say that the speed of light would be greater for someone outside the train compared to someone inside the train. But we know that the speed of light needs to be a constant following Einstein's first postulate. So if the distance traveled by light is greater for someone outside the train, then we need to now introduce that means that longer time is taken for the person inside the train. Sorry, let me just start this over again so you guys understand better. So from outside the train, we see light traveling in a triangle rather than two straight lines. What does that mean? It means that for someone outside the train, light has traveled a greater distance. And if this has happened within the same time frame, that would indicate that light travels faster for someone outside the train compared to someone inside the train. We know that's not true because Einstein's first postulate says that the speed of light has to be constant. So if the speed has to be constant and we know distance is greater for someone outside the train, then for someone outside the train, the time taken for light to travel that distance also has to be greater. So this is where the trippiness comes in. So this is where, if you think back to if you guys have seen the movie Interstellar, you know how you go into a black hole or something and then 30 years have passed even though 3 seconds have only passed for the guys inside the spaceship. That is where those concepts come from. So for someone outside the train then to keep the speed of light a constant, for someone outside the train, a longer time has been taken for a single tick in the light clock. So the time taken for someone outside the train is greater than the time taken for someone inside the train. That's what that thing sort of means. And so now let's keep going to the mathematical way of representing this, and we represent this through time dilation. So this is what the equation with time dilation looks like. You will have it in your data sheet. So it looks like this. So we have proper time, which is the time in the reference frame at rest relative to the clock time. So proper time is like the actual time that is taken. So if someone inside the train measures the time taken for light to go up and down, then that's proper time. Measured time is a time that's measured by the observer, which will be greater than proper time because for the speed of light to stay constant, the measured time for someone outside that frame of reference has to be greater. So measured time has to be greater than proper time following time dilation, and we have 1 minus v squared over c squared. So the velocity of the moving frame divided by the speed of light squared. So that's kind of what that looks like. We also have now length contraction. So time becomes relative for different frames of references. Same way, length also becomes relative as well. So we have length contraction. So the faster we move, so now let's say we can see outside. So we're not in a hollow white cube, we're in a clear white cube, right? So we can see the outside world. The faster I go, the more contracted the outside seems to be. So the faster I go, that means, so basically the faster I go, relative to me, I see the outside world. So if I'm traveling at 0.5 c, relative to myself, I'm stationary, but relative to me, the outside world is moving at 0.5 c. Even though I'm the one that's moving, from my perspective, the outside world is traveling at 0.5 c. So if the outside world is traveling at 0.5 c, then I'll see that the outside world is getting contracted. Same way for someone in the outside world, they'll see me traveling at 0.5 c, so I'll appear contracted to someone in the outside world. So how do we express that? Well, instead of time being dilated, instead of time being greater now, we have length being contracted, so length being less. How do we show that? Well, we have L naught, which is proper length. So this is the length in the reference frame at rest relative to the object. And we also have measured length. So measured length is like the length measured by the observer. So the proper length is like, so if I'm measuring so if I'm in the cube moving at 0.5 c, if I now measure the cube to have like, like a side length of like 1 meter or 2 meters, for example, then proper length will be 2 meters. And the measured length will be, so from someone from the outside world will measure the length of that cube to be 2 root 0.5 c squared divided by 1 c squared. That'll be 1 meter basically. So someone from the outside world, if I'm moving at 0.5 c, someone from the outside world would measure the length of my cube to be 1 meter, even though the actual length of my cube will be 2 meters. So that's how length contraction works. So the hardest part of questions involving relativity is understanding that these results, this is like basically inputting the results that we have and like deciding which one is the relativistic quantity and which one is the rest quantity. So we need to remember that everything is relative to everything else, right? There is no absolute frame of reference, because like there's always a frame of reference that acts relative to another frame of reference. That's just the reality. So if I'm measuring the length of the spaceship at 0.2 c, then my frame of reference is relativistic because it is moving with respect to me. So if I'm inside the spaceship, my reference frame is the rest frame because there's no relative motion involved. So if I'm inside the spaceship or I'm inside the cube, then whatever I measure is the rest frame, or like L naught basically. And if I'm outside the spaceship, whatever I measure is the measured length. So let's do a question now. This is quite important in terms of understanding what's happening. So what do we have? Well, we have a next-gen spacecraft developed by NASA has a rest length of 50 meters. The craft can reach speeds of 0.2 c. What would be its length while traveling at this speed as measured by someone back on Earth? So if I'm back on Earth, then I don't have the proper length, right? I have a measured length. So to do part A, we have the equation and we sub in the value. So we have a proper length of 50 meters because at rest it has 50 meters. So the real length is 50 meters, so it's L naught is 50 meters. My velocity is 0.2 c. So now all I have to do is sub in the value. So I do 50 root 1 minus 0.2 c over c squared. So I do 50 root 1 minus 0.2 squared to get a value of 48.989 meters, which is approximately 49 meters to two significant figures. So that's how we do part A. What if it was someone on the craft? Well, let's think about this. So at rest, the length is 50 meters. If I'm on the craft now, relative to myself, like I'm in the frame of reference of the craft, right? So like from the frame of reference of the craft, it's still 50 meters. So if I'm on the craft, then I'm in an inertial frame of reference of the craft, right? So in my perspective, the craft isn't moving at all. So from my perspective, the craft is at rest. So if the craft is at rest from my perspective, because I'm in the same inertial frame of reference as the craft, then I would measure the craft to be 50 meters as well, right? Whereas with someone on Earth, they'll be moving with respect to the craft, or the craft will be moving with respect to them. And so they will measure a measured length, whereas I will measure the observed length, or the actual length, basically. So that's how that would work. So for part B, my answer is 50 meters. For part A, my answer is around 49 meters. So that's how you would answer this relativistic motion question. And some more information is, we can and have proved using experiments long after Einstein first formulated the theory that like the concept of special relativity does exist. So a couple of things is, we've observed the change in lifetime of high-speed particles like muons. We've also done atomic clock experiments where we've flown clocks around the Earth at different speeds to show that time would be dilated on some of the clocks. So that is like an experimental observation of time dilation. And we also have the concepts of the fact that we can't accelerate things to go faster than the speed of light, no matter how hard we try. And we'll go through this a bit later. We also have the relativistic Doppler effect. So let's go through muon decay, which is this first dot point saying that the observed change in lifetime of high-speed particles, muons, that shows the concepts of special relativity or time dilation. So what are muons? Muons are tiny particles produced in space, and they're produced around 10 10 to the 4 meters above, or like 10 kilometers or 10 to the power 4 meters above the Earth. And the average decay of these muons is 2.2 times 10 to the power negative 6 seconds. And they travel at 0.98 c. So if they only exist for 0.98 times the speed of light, if they only travel at 0.98 times the speed of light and they exist for 2.2 times 10 to the power negative 6 seconds, then they should be able to travel. They should be able to travel 646 meters before they completely decay. So most muons will travel 646 meters before they decay in non-relativistic circumstances, as you can see over here. So 0.98 times 3 times 10 to the power 8 times 2.2 times 10 to the power negative 6. Normally, they'll be able to travel 646.8 meters before they die. But scientists found them much closer to the Earth's surface thanks to special relativity. So let's think about how this works, right? So they travel at 0.98 c. So let me just quickly check. So yeah. So if they are traveling at 0.98 c, then they're traveling at relativistic speed. So this is where special relativity will become quite obvious. That's where relativistic speeds comes in. So these are speeds where the differences made by special relativity become quite obvious. So if they're traveling at 0.98 c with respect to Earth, right? If they're traveling at 0.98 c, then our measured time of their 2.2 times 10 to the power negative 6 seconds will be dilated. So from the perspective of a muon, it will still travel. It will still have a half-life of 2.2 times 10 to the power negative 6 seconds. But from the perspective of the muon, right, the length it has to travel is going to be very dilated, right? So the length it has to travel is going to be contracted. So the length contraction and time dilation both apply here. They always both apply. So from the muon's perspective, it has a half-life of 2.2 times 10 to the power negative 6 seconds, but the length it has to travel to reach Earth's surface is going to be very contracted. So this distance of 10,000 kilometers is going to be very contracted, right? So it's the distance from the muon's perspective is going to be 10,000 kilometers root. And if we go through the length contraction formula, we get 1 minus v squared c squared. So 1 minus 0.98 squared, 1. So the length it has to travel is going to be 1.9 kilometers-ish. So this 10 kilometers becomes 2 kilometers from the muon's perspective. So it has to travel a lot less distance than it actually does, right? So within those 2.26 seconds from the muon's perspective, it's reached a much closer distance to Earth. So now if let's look at it from the perspective of time dilation. So from the Earth's perspective, it's traveling at 0.98 c. It's traveling at relativistic speeds. So the time, time would be dilated. So the time it travels before it decays completely will be dilated, right? So the time it takes before it decays completely is going to be 2.2 times 10 to the power negative 6. Using that formula, we have root 1 minus 0.98 squared over 1 squared to get a value of 1.15 or 1.105 times 10 to the power negative 5. So its average decay now is going to be a lot longer. So the time it takes to fully decay from our perspective is going to be a lot more dilated or a lot longer. Same way from the other perspective, from the muon's perspective, the distance it has to travel is going to be a lot less because length is going to be contracted, although their half-life remains the same from the muon's perspective. So from the perspective of an observer on Earth, the time taken for the muon to decay is dilated. So the proper time of decay is taken from the frame of reference at rest. So the proper time for decay is 2.2 times 10 to the power negative 6. And the lifetime of a moving muon from the Earth's perspective is then 1.105 times 10 to the power negative 5, following us plugging everything into the equation. So this value divided by root 1 minus v squared over c squared. So let's go through a question then. So a radioactive particle has a half-life of 2.5 microseconds while at rest in a laboratory. So its proper time, or the proper time for this equation, will be 2.5 microseconds. This same particle is accelerated to a high speed by a particle accelerator, increasing its half-life to 10 microseconds. So the dilated time is 10 microseconds. The proper time is 2.5 microseconds. How fast was it traveling relative to the observer? So all we have to do is we just have to plug it into the equation. So we have the equation over here. We have our data. So 2.5 times 10 to the power negative 6, which is t naught, proper time. And observed time is 10 times 10 to the power negative 6. So now let's rearrange this equation to make v the subject. So we want velocity, so let's make v the subject. So I made this denominator the subject, and then I squared both sides to remove the square root. Then I shifted everything around. So I shifted this to the right hand side, and I moved this to the left hand side, and then I multiplied everything by c squared, and then I square rooted everything to make my velocity the subject. And then I subbed in all the values. So I subbed in 3 times 10 to the power of 8 squared, multiplied by 1 minus 2.5 times 10 to the power of negative 6 divided by 10 times 10 to the power of negative 6 squared, to get a value of 2.904 times 10 to the power of 8 meters per second, or around 2.9 times 10 to the power of 8 meters per second. So very close to the speed of light, hence why our dilated time is approximately 4 times greater than our proper time. So it's very close to the speed of light. And the closer we get, the more our dilated time is going to be. So let's now look at the concept of relativistic momentum. So this is the concept that tells us, so it's like the third or second dot point, which tells us that the closer we get to the speed of light, the more and more energy that we need. So the closer we get to the speed of light, the closer to infinity energy that we need. So if we to achieve the speed of light, we kind of need infinite energy. So there's an asymptote at the speed of light. So the concept of relativistic momentum is taken from the concept of momentum itself, and it's adjusted for the effects of special relativity. So the concept of relativistic mass, the concept of relativistic mass is what I think you guys did in the previous syllabus, so it's not relevant right now. So right now we do relativistic momentum. So the relativistic momentum is done using this formula. So the closer we get to the speed of light, the greater our momentum is going to be. And then following this equation, what it looks like is our momentum is basically going to be infinity when we reach the speed of light, right? And it poses a limit on velocity, because now if v is equal to c, then the denominator is going to be 0, right? And so mathematically, we can't have a denominator of 0. So it will asymptote at infinity as v approaches c, or as our velocity approaches the speed of light, our momentum will asymptote as infinity. And momentum is has a relationship with energy, right? So to achieve a greater momentum, we need to supply greater energy, and so we need to supply basically infinite energy for infinite momentum. So the greater we get to the speed of light, the infinite energy the greater amount of energy that we need to supply, and it asymptotes at infinity. And because we need to supply infinite energy for something to reach the speed of light, we have a cap on how fast we can go, basically. And so it also violates the law of conservation of energy, because we can't supply infinite energy to a substance. So we have a hard set limit on how fast something can go, which is at the speed of light. And this is what it looks like. So using Newtonian physics or the classical physics, we get P is equal to mv. So it just goes up like this. So the momentum required is mc, which is not too much, right? Or it is a lot, but it's doable to a certain extent. But using our understanding of relativistic physics or relativistic momentum, we can now see that as we approach c, our momentum asymptotes at infinity. So this is special relativity. It's a very tricky concept to get in your head. It's okay if it doesn't make complete sense right now. You guys can watch a couple videos on YouTube on how to, you can watch this video over here, or search up simple relativity to understand it better. And you can also pretend that you're Einstein, start stepping through the logic of the thought experiment. So one important thing is, make sure you guys remember and understand the train thought experiment and how that worked, right? So it's that concept of different distances. So a couple questions that they can ask you is, they can ask you to mathematically show how the concept of time dilation came to be. So they can ask you to derive the concepts of time dilation or length contraction. It's not too hard. It's just the concepts of the train, the train thought experiment, where light would travel a greater distance from someone outside the train. You just use Pythagoras to show that it would be a greater distance. And then just make sure, in terms of getting confident with answering special relativity questions, make sure if you come across a hard question that you get wrong or you can't answer, explain or discuss or argue this with your friends, because you guys would have different perspectives on this, and your friend might be have a correct way of looking at this. Because as I mentioned before, the hardest part about special relativity questions is identifying which one is the relativistic momentum and which one is or which one is the relativistic value or the contracted or dilated value, and which one is the actual, the proper time, length, or mass, basically. So that is the hardest part of answering special relativity questions. So for our final topic, let's go through the mass energy equivalence, which you will cover more in module 8. So the mass energy equivalence, E equals mc squared, is basically Einstein finding a relationship between energy and mass. So he basically said that every 1 kilogram of mass, so any amount of mass will contain a certain amount of energy, basically saying that 1 kilogram of mass contains 9 billion joules of energy, so a lot of energy, right? That's basically kind of what he said. So there's a relationship between energy and mass. Energy can be converted into mass, same way mass can be converted into energy. So this is the mass energy equivalent. So let's say how much mass would be required to generate 1 kilojoule of electrical energy. Assume that mass can be converted via a 5% efficiency. So if we write down the equation now, E equals mc squared, then for a 5% efficiency, we can rearrange this equation to do at 5% efficiency, we'll have m times 0.05, which is a 5%, is equal to E over c squared, which we can now sub in the values for 1000 over 3 times 10 to the power of 8 squared to get a value for mass of approximately 2.2 times 10 to the power of negative 13 kilograms. So a very, very minute and small amount of energy. That's all we need to generate 1 kilojoule of energy. So you can see, like, stars that are combusting these thousands of kilograms or thousands upon thousands of kilos of mass, basically, and turning it into energy. They're consuming or they're producing a lot of energy. So these stars, and we'll go through this and you'll explain this more or examine this more in module 8 on your final term of physics. But this is basically a very simple application of Einstein's mass energy equivalence, or this equation of E equals mc squared. So let's go through a quick overview of what we've done. So in our first block, we looked at the development of the model of light, so the different models. So we've gone through the corpuscular model lost, the wave model 1. Then we went through the wave model and the photon model 1, wave model lost. So you can see now, as scientists, we are continuously evolving our understanding and our models of phenomena based on experimental evidence that we get. We also looked at wave behaviors, so Young's double slit experiment, diffraction, interference. We looked at historical methods for determining the speed of light. We looked at blackbody radiation, which segued us into the photoelectric effect and the ultraviolet catastrophe. Then we looked at spectral analysis and how we can analyze different things about stars using our understanding of photons and spectra. We then looked at Einstein's two postulates, special relativity along with that. And then finally, we touched on Einstein's energy mass equivalence. So a lot to cover in 2 hours, but I hope you guys have a general understanding of what happens. I know many of you guys might still be confused with special relativity. It is a very confusing concept to wrap your head around, but the understanding that thought experiment will make a lot more sense. But yeah, if you guys have any more questions, make sure to put them down in the live Q&A section. And even after the lecture, if you have questions, you guys can go to the 800 discussion section, the online Q&A, where current or past students like me can answer your questions for you. So yeah, I hope you guys enjoyed this lecture. I hope you guys got something out of it, and now you have like a general understanding or a basis, a knowledge basis for going into module 7 next week in school, I think. But yeah, thank you guys for sticking through the lecture.